Alright, welcome to video 13. This is a concept called electron shielding. So, in addition to the attraction of each electron to the nucleus, each electron experiences the repulsion due to other electrons. Now, let's go back to Coulomb's law real quick. So, the nucleus basically consists of a bunch of protons. Okay, and the electrons are negatively charged. Okay, let's pretend that we've got, some distance, doesn't really matter. This ultimately, when you multiply this out, gets you some kind of negative answer, which Coulomb's law says is attraction. Okay, that's a way of explaining, if you will, somewhat, why electrons go closer to the nucleus, why they're typically attracted there. However, keep in mind that for two electrons, they're both negative, which gets you a positive force. And in fact, actually, the smaller this distance, meaning the closer they get, the higher the repulsion is between them. So if you've got, an electron over here and an electron over here, let's pretend that they're kind of far away. They don't really care that much about each other. They're just not getting too much closer. But if you've got electron and electron, they're going to push each other away. They're going to repulse. They're going to kind of move back farther away. That's one of the basis of electron shielding. So these electron-electron repulsions basically cancel out some of the attraction of the electron to the nucleus. Ultimately, the electron experiences less attraction than it would if the other electrons were not there. We're basically saying, here's our nucleus, and you've got electrons surrounding it, all the different orbitals, etc. And we're looking at this electron out here. What we're basically saying is that the attraction towards the nucleus is weaker than if there were no other electrons. Okay, now what's happening is, yes, you've got this same attractive force, but you've also got all the other repulsive forces of the electrons pushing back at it. So as it wants to get closer to the nucleus, it gets closer to other electrons, which push it back away. I tend to also think of it as all the electrons closer kind of absorb some of the attraction. So by the time you get to the outer one, there's less attraction left. That's not exactly what happens, but if that helps clarify it, cool. Okay? So, in essence, each electron in a many-electron atom is shielded from the nucleus by the other electrons. That's where the term comes from. It's mainly referring to the electrons on the outside, but ultimately, really any electron is at least mildly shielded from the nucleus by other electrons. And again, that's because they're pushing back. The other electrons are pushing it back away, but it's as if they're shielding it from some of the attraction of the nucleus. Therefore, that outer electron, or again, whatever electron's being shielded, experiences a net attraction that is less than it would be in the absence of other electrons. Now, I know we said this before, but just making sure you got this. It basically experiences a less net attraction. Now, difference between net and gross, in case you'd like to know, is gross is basically what overall is actually happening, and net is really what you end up with. So what that means is that there's still the same gross attraction for that electron, again, towards the nucleus. Technically, they're the same charge, they're the same distance. Coulomb's law says there's the same amount of force. Net attraction, though, also factors in the other repulsions. So it's as if you've got a weaker attraction. Okay? That is especially true for the valence electrons, as all the core electrons shield the valence electrons from the full electrostatic attraction of the nucleus. Please keep this concept in mind. This explains atomic radius. This explains ionization energy. This somewhat explains electronegativity. It explains almost all the trends we're going to be talking about. So that's electron shielding. Thanks for watching.